Hi and welcome to this tutorial on electrons in atoms. So in our previous tutorial, we learnt about the principles of the time of flight mass spectrometer. So we learned about ionization, acceleration, ionic drift and ion detection, and we learned about how to interpret the mass spectrum graph too. So in this session, we are having a look at electron shells, subshells, the arrangement of electrons and electron orbitals. So there's quite a lot of slight differences in the definitions. You need to be really confident with what the differences are between these different terms. So let's broadly have a look then at our structure. So we're going to be looking not at the nucleus, but at the electrons surrounding it, how they're arranged and where they're arranged. So we know that electrons move in electron shells around the central nucleus here. And the different shells represent different energy levels. So the red circle here is one energy level, yellow is another, and green is another as well. And although we're going to show this as a two-dimensional depiction, remember this is three-dimensional. So we can also think of this in terms of spheres, but we will look in more detail about our subshells as well. So even that's not accurate enough. But we do show a lot of these two-dimensional depictions. And these are just models. They represent those energy levels quite clearly for us. So we can see that they've got fixed energies. So in the red, those two electrons are at a fixed energy, and each electron shell has a particular energy level. And electrons can only have one of the fixed energy levels of the shells. We're not going to see electrons in between the red and the yellow. They're going to be at the energy level of the red circle, at the energy level of the yellow, not in between. Okay, so shell 1 has its own energy level, shell 2 does, and shell 3 does. The energy level of the electron shells increases as you move away from the nucleus. So we can see the electron shell that's further from the nucleus, like the green shell here, has got a higher energy level than the two below it. And each electron shell has a principal quantum number. And that word sounds really big and confusing, but it's not. The principal quantum number is just the number given to each electron shell. Okay, so shell 1, which is, actually let's keep that. So shell 1 will be the red, the center one, is going to be, has a principal quantum number of 1. Shell 2 is my yellow shell, and that's got a principal quantum number of 2. And shell 3, which is my green shell that you can see, it's got a principal quantum number of 3. And then we've got two main words that we need to know the difference between. We've got subshells and we've got orbitals, and we're not to get them confused. Looking at subshells in more detail, one or more orbitals in the same shell which have the same energy levels. So we learned that electrons can split into shells, each with their own energy level, and that's what we were talking about in the previous slides. Well, electrons within each shell can be further split into mini subshells. So we had red, yellow, then green in the previous image, but if we looked in more detail at the green, the outermost, those electrons are further split into subshells, meaning the electrons in the same shell do not all have the same energy level. And there are 4 different subshells that we need to know about. We've got S, P, those ones that we're going to come across a lot. We might sometimes come across D, and we won't really come across F very often, but it's good to know that they're there. So S, P, D, and F. And you might want to create an acronym to help you remember those 4. Electrons in the same shell do not have identical energy levels, as I just said. So when we talk about subshell, we're going to be talking about, I'm probably going to refer to the colours of the circles. So shell 1, this red shell here, has only one type of subshell, the S. Okay, so both of these electrons can only be in one type. We talked about S, P, D, and F. They've only got S. Shell 2 has got 2 different types of subshells. It's got S, and it's also got P. Shell 3 has got 3 types of subshells. So the green one on the outside, we can find electrons in the S, the P, and the D subshells. So think of shells like floors on a property. So for red, that is the stairs to the between the first floor, and then the yellow is our second floor, and the green is the stairs to our third floor. But within those stairs, helping us to get from each level, we can have the energy levels between each individual stair on the case. So we've got the difference between the floors overall first floor, second floor, third floor, for example. And then we've got the different energy levels of the stairs. Those are the subshells. And here's another infographic that helps you understand it even more. So we're getting rid of the model with the 2D circles, and we're actually looking at those energy levels. So lower energy subshells are closer to the nucleus. So the red circle, for example, in the previous slide. And then the quantum number obviously increases as we move further away, and the energy level increases as we move further away from the nucleus. So the 3s subshell has the lowest energy in shell 3. So if we look at the 3s, our yellow circles represent our third shell, and we can see the 3s is the lowest energy level out of the third shell, out of the yellows. It's the lowest down. It's closest to the nucleus. That's why. It's almost like stairs. You can almost see that sort of stair idea. You don't get energy in between. They are quite strictly on their stairs. And the 3D subshell has the highest energy level in the shell 3 because it contains electrons that are furthest away from the nucleus, 3D. So as we move to shells with the higher quantum numbers, they are further away from the nucleus, as I said, and actually you start to get overlap of the subshells. Okay, so the energy gap between the successive shells gets smaller and smaller and smaller. So you can see there's a big gap between 1s and 2s here, but up here we start to get very, very small gaps. You will see that shell 3 has an overall lower energy than shell 4, my greens, but within that there's actually an overlap. We can also see that the 4s has actually got a lower energy than the 3d. So we're getting this overlap going on, but overall the third shell's got a lower overall energy than the fourth shell. Let's look at S and P subshells in more detail. So we've got S, P, D and F. S and P you need to be able to draw. You don't need to be able to draw D and F, at least for OCR anyway. So here we've got a drawing of an S subshell. Now it's really important in the exam, if you're asked to draw it, yes, it's just a circle, fine, but you need to add your axes lines on and label them. So you need to put a line for your Y, a line for your X, and then a diagonal for your Z. It shows that it's three-dimensional. It's a three-dimensional sphere. We're drawing a 2D image. We need to realize that this is actually in 3D, and they are spheres of probability of where you're going to find electrons. So we could find electrons most probably anywhere within this sphere, within the blue area, and not really outside. And then we've got our P subshells. Now, they're actually arranged into 3 types. So 2 electrons can go into S, 2 can go into PX, 2 into PY, and 2 into PZ. So overall, the P subshell's got 6 electrons. And you can call this a figure of 8 or an hourglass configuration. And again, I'm drawing my axes, my X, Y, and Z, and I've got that figure of 8 going over my X, hence it's PX. PY is a figure of 8 going over the Y, and PZ is going over the Z. Okay, and you can see we've got the nucleus represented by the red dot in the center. So again, these, and they're also called dumbbells. That is what sometimes you'll hear people referring to the P suborbital as. And we are just showing the blue shaded area is areas where electrons are most likely to be found. It's probability. And each subshell can hold a specific number of electrons. So each subshell, in each subshell, the electrons are held in orbitals, and each orbital can hold 2 electrons. So for example, we had our S. Now S can have 2 electrons found within that probability, of course, Y, X, Z, or if we picked one of the p orbital types. So if I picked PZ, then 2 electrons can be found within that, within this area here. I could also have PX and PY. Each of those is going to have a maximum of 2 electrons. So overall, when we're talking about P, we could have 6 in total, 2 in each. So this table is going to represent the properties of each type of subshell. So remember, we had S, P, D, and F, signifying as we go further and further away from the nucleus. So the number of orbitals in S, we're just going to have 1. The number of orbitals in P, we've got 3. Remember, I showed you PX, PY, and PZ. We don't have to draw D, but the number of orbitals, just so you know, is 5. And the number of orbitals for F is 7. So if each orbital can have a maximum of 2 electrons, then to work out the maximum number of electrons in that subshell, I just need to times each of those numbers by 2. So therefore we can have 2 electrons for the S, 6 electrons for the P, 10 for D, and 14 for F. So using the information in the table that we just looked at, we can then calculate the number of electrons that each shell can hold. So if we look at the first shell, we know that that's only going to be a 1s. So we call it 1s. And it's an S subshell, so it's 1 orbital, so it can hold 2 electrons. Then if we look at the second shell, this is going to be a 2s and a 2p. Okay, so my S subshell is 1 orbital, so that's going to contribute 2 electrons. And my P subshells, they are 3 orbitals, remember in the previous slide? And so that is 6 electrons. So in total, 2 plus 6 is 8. And that's where at GCSE you learnt that the first shell's got 2 electrons, then 8, 8, 8, 8. Now that's not strictly true. To start with, yes, 2, then 8, but after that we might start getting slightly different numbers. But you have come across these, these first few numbers before, so we're just learning about where they came from and adding to that knowledge. It doesn't mean your GCSE knowledge is wrong, we're just adding more and more information. So the third orbital, we're going to have a 3s, a 3p, and then a 3d. Like I said, F, we're not going to really talk about that at A level. So the S is going to be 1 orbital, and that's going to be 2 electrons. The P's are going to be 3 orbitals, and so therefore that's 6 electrons. And remember the D, that's 5 orbitals, and then we times that by 2 because each orbital can have 2 electrons. That's 10. So in total we could have 18 electrons in that third shell. So again, let's have a look at this. The number of shells in the first, the number of subshells is 1. The second we had 2 types, we had S and P. In the third we had S, P and D. And in the fourth we had S, P, D, and we would have F as well. Okay, so the number of orbitals that we would have, S is only 1 orbital, P is 3, D is 5, and F is 7. When we talk about orbitals, we're talking about a volume, because it's 3D, a volume of space that electrons are most likely to be found in. So each orbital, of course, contains a maximum of 2 electrons. These electrons, they actually spin in opposite directions. That's what I'm representing here. Okay, so as they spin on their axis, the moving charge results in the formation of a magnetic field. So in each orbital, one electron is going to spin up and the other one is going to spin down. And whilst different shells have got different energy levels, as we learned about right at the start, the different subshells also have different energy levels. Remember the difference between those individual steps between each floor. And different orbitals within the same subshell have the same energy level. So the 2 opposite spins in the PY will have the same energy level. The 2 opposite spins in the PX will have the same energy level. All the P's will have the same energy levels, as you can see here. So all the 2 P's, PY, PX, and PZ will have the same energy level.